Welcome back everyone. So in the previous video we discussed about the group velocity and phase velocity, and at the end we came to the conclusion that there were some drawbacks of the group velocity, and these were fulfilled by the Heisenberg Uncertainty Principle. So today we are going to discuss the Heisenberg Uncertainty Principle. So basically in classical mechanics we can determine the position and momentum of macroscopic bodies simultaneously with perfect accuracy from its initial position, momentum and the forces acting upon it. But in quantum mechanics a particle is represented by a wave group. As I have discussed in the group velocity, that particle velocity is actually a packet of wave. So a particle is represented by a wave group. So a wave cannot be localized, and what is meant by this line, wave cannot be localized, that is, for example, if we jerk a rope we will get some waves in the rope, and the waves may be in their uh, periodic manner or not. But the question is, if I ask you where is the wave in that rope, you can direct me to a fixed position. That is, say, you can't say me that this wave is present in the 7th position or 8th position, but you can tell me that yes, the wave is inside the range from 8 to 10. That is, we are saying that the wave is localized. What I meant to say, that we can find the range of the wave, but we can't find the fixed position. So that range is specified for that one single wave. That is why waves are localized. Now if I say to find out the wavelength, you will say that wave is not complete, so how can I find the wavelength? Thus you can see that you cannot find the wavelength or the position simultaneously. And what I am saying, this all thing, that all is for the rope, and the same goes for the in case of quantum mechanics too. In case of quantum mechanics, since particles are combined in a wave packet, so they also carry the same characteristic of this single wave. Okay, so now in the second fact, I have written that if we do not exactly know the position of a quantum particle, we cannot predict its future. Say we are considering the particle to be v. So if the particle do not exactly know the position of the of its quantum particle, so it cannot predict its future. So it actually means that if we do not have the initial conditions, we cannot predict the future of the particle. The future means the velocity and the position it is going to attempt after another period of time. So, and the next one is I've written, according to Bohr and Heisenberg, the probabilistic wave is the fundamental one in quantum physics, and determinism must be discarded. So in quantum mechanics you cannot be sure about a particle. That is, you can tell that a particle can be there, but it is probabilistic, and it is the fundamental nature of quantum mechanics. In short, we can say that whatever we discussed up to this, that we cannot find the exact location but can find the range of the particular wave. More precisely, to describe this thing, we can demonstrate it by diagram. See, so there is a small wave and there is this large wave. So here the position of this wave is del x, and here del x is well defined, that is less uncertainty. And in this wave the del x is not so well defined, but the wavelength is well defined, since we can we know the at least the origin and the end point of this wave. So, and so is the momentum. So you can see How, when we know that the position is well defined, we cannot define the wavelength at the same time, but when the position is not so well defined, we can define the wavelength and momentum at the same time. From the de Broglie relation, we know that lambda is equals to h by p, so p becomes h by lambda. So P is not so well defined. Therefore, the momentum and position of a moving particle cannot be measured simultaneously with perfect accuracy, and that is what Heisenberg stated in his principle. So thus, when a microparticle is in motion with a velocity comparable to the velocity of light, which we have compared while discussing the group velocity and wave velocity, its position can be anywhere within the wave packet. Hence, there will be an uncertainty in specifying the position of the particle, and at the same time, a wave packet consists of range of wavelengths. Thus, from this de Broglie relation, there will also be an uncertainty in the measurements of momentum of the microparticle. So I hope this is clear to you what Heisenberg actually defined in his principle, and why this principle is called the Heisenberg Uncertainty Principle. That the what that word uncertainty actually defines. That is, we cannot define these momentum and position at the same time. There always there is a uncertainty in them. So Werner Heisenberg was the name of the scientist who in 1927 enunciated the principle of uncertainty. So from exam point of view, we can write that Heisenberg uncertainty principle states that the product of uncertainties in the simultaneous measurement of the position and momentum of a particle is equal to or greater than h, which is h by 2 pi. That is del x del px greater than is equals to h, and it is applicable for all direction. Del x is the position and del px is the momentum. Or for all direction, I meant to say that it can be del y, del py greater than is equals to h, and for all. So you can see the problem is not of finding the exact location, the problem lies in the simultaneous finding. In fact, you can measure this del px and del py at the same time, but you cannot measure del x del px at the same time, or del y del py at the same time. And one more thing, let me tell you, position and momentum are conjugated variables. So position and momentum are conjugated variables. This is clear to you. And there are some physical interpretations of Heisenberg uncertainty relation. That is, as I have told you, that we cannot measure this simultaneously. So the first one is, if we can measure the position of a particle accurately, the uncertainty in measurement of momentum at the same instant becomes infinite, and vice versa. So that was all related to the Heisenberg uncertainty principle. So if you like our videos, please like and subscribe to our channel. Thank you for watching.